Good morning, everyone. Today with us we have Monica Nonino. Monica was a former PhD student here in CISA under the MATLAB group, and now she's in Vienna and she's waiting to be a postdoc here in November. So today she will talk about her PhD project, let's say, that she carried out here in CISA, segregated reduced order models for fluid structure interaction problems. Thank you, Monica.
Okay, so thank you, Maria, for the introduction. So before we begin, let me show you the outline of the presentation. So I'm sorry for those of you who are already quite familiar with the reduced basis method, but for those of you who don't work with it, I will give you a short introduction on the reduced basis method. Then I will show you a formalism, which is widely used in the framework of fluid structure interaction problems, which is the arbitrary Lagrangian Eulerian formulation. And then we will move on to the actual topic of this talk, which is partitioned algorithms for fluid structure interaction problems. And since we have time, and because I think it's nice to see at least once, I'm going to show you a particular numerical scheme, which is the Charinteman projection scheme for Navier-Stokes equations. And then I will present you a reduced order model, which is based on partitioned algorithms. And we will see how this reduction method performs on two test cases. The first one is a non-parametric fluid structure interaction problem. And the second one is a geometrically parameterized FSI problem. And then we will move on to some conclusions. So, onto the reduced basis method. The reduced basis method is an approximation method which is particularly useful for fast and reliable simulations of solutions of parameterized PDEs. And usually these PDEs arise from industrial applications, biomedical applications, and so on and so forth. And these problems depend on a large number of physical and or geometrical parameters. And in general, to solving these PDEs requires both a large amount of computational time and a large amount of computer memory. So say that you were able to obtain the simulation of a solution of a problem of interest for a given set of values of the parameters in the problem. Now the question is, what happens if you are interested in changing one or more of these parameters? Like, do you have to compute everything from scratch? And the answer is no, and this is where the reduced basis method comes into play. So as I said, you have a high number of parameters, both geometrical and physical, belonging to a parameter space calligraphic P. You start with your original problem, and then we have a first discretization step, which can be carried out with the finite element method, but also finite volumes, spectral element methods, and whatever you want. And here, the solution, which in the reduced basis community is called snapshot, belongs to a space X calligraphic N of dimension calligraphic N. This is the expensive part of the algorithm. So you compute a set of snapshots for given values of the parameters. And then the key ingredient is to be able to extract from this set of snapshots a set of smaller cardinality of reduced basis. And then we basically say that for any new value of the parameters in the problem, we approximate the solution of the original problem with a linear combination of these basis functions. So, of course, the question that pops into the mind of the student is, how can we obtain this reduced basis in such a way that we are able to say, okay, for any new value of the parameter in the problem, we can approximate the solution with something as simple as a linear combination of basis functions. And the answer is, you can adopt two strategies. you can either use a greedy algorithm or a proper orthogonal decomposition. So the greedy algorithm I did not use during my PhD because it usually requires the availability of an a posteriori error estimator, which is something extremely difficult to have, and it is even more difficult for fluid structure interaction problems. So I worked with the other alternative, which is the proper orthogonal decomposition. So basically, this is the POD in a nutshell. So you start by discretizing the parameter space, and you obtain a training set of n-train values of the parameters. Then for each of the parameters in the training set, you compute the snapshot. Then the first thing that you do is you build the correlation matrix whose entries are basically just the scalar product between two snapshots. Then you solve an eigenvalue eigenvector problem, and you order the eigenvalues of that you found by decreasing order of magnitude. And then you say that the reduced bases are a linear combination of these snapshots with coefficients that are the entries of the eigenvectors that you found. And this is how you build the reduced basis set with the proper orthogonal decomposition. So now let's move to the topic of interest of my PhD project, which is fluid structure interaction problems. So this is the, let's say, general form of a multiphysics problem. Say that you are in a two-dimensional setting. As you can see in the picture, you have in blue the fluid domain and in red the solid domain. And as you can see, both domains depend on time, on the time t, because usually we are considering time-dependent problems. So in the system below, you can recognize the incompressible Navier-Stokes equations. And then the third equation is the problem for the solid domain. So here I just put the linear elasticity problem, but you can also work with, I don't know, the generalized string equation or linear elasticity, whatever you want. And I would like you to notice that the fluid problem is formulated on a domain which depends on the time, whereas the solid problem is already formulated on a domain which is time independent, and that is the solid reference configuration. So this represents an important fact in the framework of fluid structure interaction problems, because usually to describe the motion of fluid, you adopt the so-called Eulerian description of the motion. So the equations of the fluid are formulated on a time-dependent domain. Whereas for the solid problem, you can adopt the Lagrangian description of the motion. So you can formulate the problem on a reference configuration which is time independent. So of course the question is, how can we obtain a uniform formulation for the entire system? And the answer is that we can think about mapping the Navier-Stokes equations back onto an arbitrary time-independent configuration. So usually this fluid configuration is arbitrary, as I said, but since we are taking as a solid reference configuration the solid domain at the starting time t equals 0, we can also take as the fluid reference configuration the fluid domain at the starting time. And this gives rise to the well-known arbitrary Lagrangian Eulerian formulation. So in order to be able to do this, we define a deformation map, which goes from the reference configuration to the original configuration at time t. And as you can see, this deformation map is basically an identity mapping plus a displacement. So this displacement is the solid displacement if the point falls in the solid reference configuration. Whereas if the point you are considering is in the fluid reference configuration, then it is more difficult to understand what the displacement of a fluid is. And indeed, there are multiple ways on how to define dF. So I always work with the harmonic extension. So dF is defined as an harmonic extension of the solid displacement on the whole fluid domain. But you can also work with another linear elasticity problem, or you can also define dF with a biharmonic extension. But for our test cases, this was more than enough. And so this is the final formulation within the arbitrary Lagrangian Eulerian formalism. So starting from the bottom of the system, you have, as you see, the linear elasticity problem for the solid. Then in pink, we have an additional equation, which is due to the Ailey formulation. And then we have the Navier-Stokes equations with additional terms. And here, F is the gradient of the deformation map, and J is the determinant of F. And of course, since we want a coupled system, we have to have some coupling conditions. So these are in pink, the continuity of the displacement at the fluid structure interaction interface, which is basically the part of the domain which is in common to the fluid and to the solid. Then in blue, we have the continuity of the velocity at the interface. And in green, we have an action-reaction principle, which basically says that the stress of the fluid and of the solid have to balance at the interface. So enough with the formalism. Now, from the numerical point of view, how can we address a fluid structure interaction problem? So you can use two main class of algorithms. So the first one is partitioned or segregated algorithms, where basically the idea is that you solve separately the fluid and the solid problem. And these algorithms are further divided into three categories. So we have the explicit partitioned algorithms, where we treat explicitly with respect to time the coupling conditions. And these kind of algorithms turn out to be unstable under certain conditions on the physical parameters of the fluid and of the solid, and on the geometrical configuration of the problem. Then we have implicit algorithms, where we treat implicitly with respect to time the coupling conditions, and this of course leads to a higher computational cost. Or we can use a semi-implicit coupling, where we treat some coupling conditions implicitly and some other explicitly. Or alternatively, you can use monolithic algorithms, where you solve all at once the fluid and the solid problem. So these algorithms are more stable, but the drawback is that they require an ad hoc software, which is able to handle at the same time the fluid and the solid problem. And also, in general, it is more difficult to impose the coupling conditions at the fluid structure interaction interface. For example, you could think about using Lagrange multipliers, but these leads to additional unknowns that have to be added to the problem formulation. So in this talk, I will present you the first class of algorithms, which is partitioned algorithms for fluid structure interaction. And this work has been carried out in collaboration with my former PhD advisor, Professor Gianluigi Rozza, my co-advisor Francesco Ballarin, and Professor Yvonne Madet. So let me present you, first of all, the test case setting. So we are in R2. In blue, we have the fluid reference configuration. In red, we have the solid reference configuration, and I hope it is visible, but in green, we have the reference fluid structure interaction interface. What I wanted to do is I wanted to simulate the bending, the behavior of the two leaflets under the influence of a fluid flowing into the channel. And to address this problem, I decided to use a Charinteman projection-based semi-implicit partitioned scheme. So starting from the end of the name, we use a partitioned algorithm. We treat decoupling conditions in a semi-implicit way, and we use the so-called Charinteman projection scheme. So now, what is the Charinteman projection scheme? Very shortly, because we will need a lot of time to talk about that. This is a frequently used method for the numerical solution of the incompressible Navier-Stokes equations. So here I just wrote the simplest of the Navier-Stokes equation. We have the incompressibility constraint and a homogeneous Dirichlet boundary condition on the whole boundary. The idea of the Charinteman projection scheme is to use a peculiar time discretization, which leads to the splitting of the original Navier-Stokes equations into two problems. So in the first problem, we consider the viscous part of the Navier-Stokes equation, and this is an elliptic problem. Whereas in the second problem, we take into account the incompressibility constraint, and we have an essentially inviscid problem. So, of course, this means that by splitting the original problem, the original Navier-Stokes equation into two sub-problems, we will have to work with two different velocities, the so-called intermediate velocity, UF, which is the velocity appearing in the first problem, so viscous part of the projection scheme, and we have an end-of-step velocity, U tilde, which is the velocity of the incompressible part of the problem. And these two velocities will have very different degrees of regularity, because the velocity of the intermediate step will belong to H1 here as 0, and the end of step velocity will belong to HDiv, which is defined in the following way. And so before presenting you the actual projection scheme, we introduce an injection operator which goes from H1 to HDiv. And with this operator, we can write the projection scheme as follows. So we have the first problem, the viscous step, which is formulated in terms of the intermediate velocity. And as you can see, we are just considering viscous terms and advection terms of the Navier-Stokes equation. And then we have the projection step, meaning the incompressible step, where we have the end of step velocity U tilde and the pressure P. And you can recognize that here we're taking care of the divergence-free condition. Actually, from the numerical point of view, we can get rid of the end of step velocity by using the following relation, and I'm not going to explain where this relation comes from, but thanks to this, we can rewrite the viscous step just in terms of the intermediate velocity F, and we can also rewrite the projection step as a problem just for the fluid pressure. And as you can see, we end up with a Poisson problem for the pressure, which of course will have suitable boundary conditions, which we will see later on. And the reason for choosing to do so, the reason for choosing to discard the end of step velocity and using a pressure Poisson formulation, actually there are a lot of reasons. From the finite element point of view, by doing this, we avoid to work with different discrete spaces for the intermediate velocity and for the end of step velocity. And also, always at the finite element level, there are very nice results that show us that we can actually work also with pairs of fluid velocity spaces and fluid pressure spaces that do not necessarily satisfy the LBB condition. And from a reduced order model point of view, the reason for using a pressure Poisson formulation is that in the online phase, we obtain a system of smaller dimension to be solved. And also, we can avoid to use a supermiser enrichment technique, which again leads to a reduction in the number of unknowns to be used in the online phase. Now, so back to the original test case. So this is the problem formulation within an arbitrary Lagrangian Eulerian setting. So as you can see, we have the Navier-Stokes equations in the fluid reference configuration. We have the harmonic extension of the solid displacement to the whole domain. We have the linear elasticity problem for the solid. And here the Cauchy stress tensor and the Piola-Kirchhoff stress tensor are both expressed in the reference configuration. So as far as the algorithm are concerned, we start with discretizing the time interval, and we use a time step of delta t. And we then introduce the discrete spaces for the fluid problem and the solid problem. So the first thing we do is we extrapolate the mesh displacement. So we solve the fluid displacement harmonic extension on the fluid reference configuration. Then we have the first step of the algorithm, which is the first problem of the Charinteman projection scheme, namely the viscous step. And here in red, I highlighted this boundary condition. So this is a non-homogeneous Dirichlet boundary condition on the FSI interface. And you can recognize that we are treating the continuity of the velocity at the interface in an explicit way because we already computed the fluid displacement in the previous step. So in order to discard this non-homogeneous boundary condition, we introduce a change of variable. So introduce a new variable zeta, which is basically a lifting. And the reason for doing this is that we can transform the condition 2.2 into an equivalent one, which is a homogeneous Dirichlet boundary condition for the new variable zeta. Then we have two sub-problems. So we have the second step of the Charinteman projection scheme, which is the pressure Poisson formulation. And we have the solid problem, so the linear elasticity. And you can see that we are treating the balance of the stresses at the interface in an implicit way. So the two sub-problems 1 and 2 are iterated between one another until a convergence criteria is satisfied. And here in pink, I put the boundary condition for the pressure Poisson formulation, which is basically a Robin transmission condition, which is rather intricate, but the important thing is that we have a constant appearing there, which is alpha Rob, which does not only depend on the physical properties of the fluid and of the structure, but it does also depend on delta t, which is the time step used in the numerical simulation. And it is this is extremely important and peculiar to partitioned schemes for these kind of fluid structure interaction problems. Then, at the reduced level point of view, we start by performing a proper orthogonal decomposition on the set of snapshots. And as you can see, since each snapshot of zeta satisfies a homogeneous boundary condition on the fluid structure interface, then also every reduced basis for zeta will satisfy the same boundary condition, and therefore any linear combination of these reduced bases will satisfy the same condition. For the fluid pressure and the solid displacement, we just perform a standard proper orthogonal decomposition. And you see that for the generation of the fluid displacement basis functions, we do not use a proper orthogonal decomposition. Instead, we decided to perform an harmonic extension of the solid displacement basis functions to the whole fluid domain reference configuration. So we can also introduce the finite dimensional space for the fluid displacement. We introduce the online variables for zeta, p, and ds. And as you can see, the fluid displacement is defined as a linear combination of the fluid displacement basis functions with coefficients that are the coefficients of the solid displacement at the previous time step. So by doing this, we are automatically satisfying the condition on the continuity of the displacement at the FSI interface. And then all the other problems, so the viscous step of the Charinteman projection scheme, the pressure Poisson formulation, the solid problem, are formulated in the same way as in the finite element step of the algorithm. The only change is that now we have to reformulate the viscous step of the Charinteman projection scheme as a function of the new variable zeta. And then once we have found zeta, we can restore to the fluid velocity online variable UF using the inverse transformation. And these are some numerical results. So at the top of the slide, you see the behavior of the fluid velocity at two different time steps. And at the bottom of the slide, you see the behavior of the solid displacement at three different time steps. And these results have been obtained using 20 modes, so 20 reduced bases for the fluid velocity and for the solid displacement. And for those of you who are interested, these are the values of the parameters and the constants used in the numerical simulation. And as you can see, I used a very small time step of the order of magnitude 10 to the minus 4 for a total number of time iterations of the algorithm of 2000. Now, the second test case is always the test case of the leaflets, but now we decided to add a geometrical parameter, mu g, which represents the length of the leaflets. So as you can understand, the problem formulation becomes even more complicated because now we are dealing with three different configurations. So starting from the left, we have the reference configuration, which is both time independent and parameter independent. Then now we have an intermediate configuration, which is still time independent, but parameter dependent. And then we have the original configuration, which is both time dependent and parameter dependent. So to go from the intermediate configuration to the original configuration, we always use the deformation map defined for the arbitrary Lagrangian Eulerian formulation. But to go from the reference configuration to the intermediate configuration, we use a shape parametrization map, which usually you can compute by yourself, or you can ask a computer to do so for you. And the introduction of a shape parametrization map gives rise to the introduction in the problem formulation of additional terms, which are G, so the gradient of the shape parametrization map, and K, which is the determinant of G. So this is the problem, the original problem formulation. So as you can see, we have the problem for the fluid displacement, which is defined on the intermediate configuration. The Navier-Stokes equations are defined in the original configuration, and the linear elasticity problem is defined in the intermediate configuration. So to obtain a uniform formulation, we pull everything back on the reference configuration, and this is what we obtain. So we have the Navier-Stokes equations in the reference configuration, and now also the linear elasticity equation has been transformed in the reference configuration. And at the bottom of the slide, we have always the coupling conditions, so the continuity of the displacement, of the velocity, and the balance of the stresses at the FSI interface. Then the algorithm that we use to address this problem is always a Charinteman projection-based semi-implicit coupling scheme. So from, let's say, the finite element point of view, the major change is the introduction of the additional terms in the problem formulation. Then the first thing we do is we discretize the parameter space, and we obtain a training set you can use any discretization that you want, but for our test case, we used an equispaced sampling for the numerical tests. And then for each value of the parameter in the training set, we compute the corresponding finite element solution. So we end up with this set of snapshots. And we then perform a proper orthogonal decomposition on this set of snapshots. And again, we decided to introduce the change of variable zeta to work with homogeneous boundary conditions. And again, we decided to implement an harmonic extension of the solid displacement to the whole domain in order to obtain the reduced basis for the fluid displacement. And then the design of the online phase of the method proceeds exactly as before. And these are the numerical results. So at the top of the slide, you see the behavior of the fluid velocity at the final time step of the simulation for two different values of the length of the leaflets. And at the bottom of the slide, you see the behavior of the solid displacement, always at the final time step of the simulation, for three different values of the length of the leaflets. So the longer the leaflet, the bigger the bending or the displacement. And these results have been obtained using 100 modes for the fluid velocity and for the solid displacement. And again, these are the values of the parameters and the constants in the problem. And again, I use the time step of 10 to the minus 4 for a total number of 800 time iterations, so a little bit less than in the non-parametric test case. And so moving on to conclusions. Of course, partitioned schemes allow you to decouple the fluid and the solid problem. And this is good because at the online level, this means that you have a better control on the number of unknowns you're going to use, and therefore on the dimension of the system that you are going to solve. And also the algorithm that I showed you, so the Charinteman projection-based semi-implicit scheme, allows you to work even at the finite element level with pair of fluid velocity, fluid pressure spaces that do not necessarily satisfy the in-fluid conditions such as P1, P1. And thanks to this, at the reduced order level, we can avoid to use a supremiser enrichment technique to obtain a good approximation of the fluid pressure. So again, this means that we have a good control on the number of unknowns that we use in the online phase of the method. And also the choice of using a pressure Poisson formulation and the choice of implementing an harmonic extension of the solid basis functions leads to a good control on the dimension of the system in the online phase. But a drawback of this procedure, which I want to underline, is the fact that because of the presence of the Robin transmission condition in the pressure Poisson formulation, we have that constant alpha Rob, which was highlighted in pink at the beginning of the presentation. And that constant, as I showed you, depends on the time step used in the numerical simulation. And the problem is that if we are using a time step that is too big, we will have stability issues. And indeed, as I showed you for our test cases, we use a time step of 10 to the minus 4. This with the partitioned procedure. But let me tell you that with a monolithic approach, so by choosing to solve at the same time, all at once, the fluid and the solid problem, with the same values of the parameter for the same test case, we can obtain good results using a time step of 10 to the minus 2, which is 2 orders of magnitudes bigger than the one we used for our test cases. So of course, as a future development, it would be really interesting and important to study alternative decoupling techniques that lead to a Robin transmission condition where if we are not able to get rid 100% of the presence of the time step in the constant alpha Rob, at least we can improve that dependence in order to be able to use bigger time steps in our simulations. Then, of course, it is important to incorporate also the empirical interpolation method because we're working in an arbitrary Lagrangian Eulerian setting. So we have, by definition, a lot of nonlinearities. And even if you want to consider, for example, a nonlinear elasticity problem, then you have additional nonlinearities. So including an empirical interpolation method would be important for the sake of the reduced order model. And yeah, I think that this is it. This is a short bibliography which comprises both studies on the Charinteman projection scheme, partitioned algorithms, arbitrary Lagrangian Eulerian formulation, fluid-structure interaction problems, and also the two softwares that I used for the numerical simulations. So I used Multiphenics to obtain numerical results at the finite element level, and then I used Urbanics to obtain the results within a reduced order model framework. And yeah, thank you for your attention.
Thank you, Monica. Thank you for the talk. So now if you have questions, you can unmute yourself and you can talk directly to the speaker. So let's see if someone has questions. Okay, actually I can start. I have a couple of questions, Monica.
Okay.
So more of them are curiosities, actually.
Okay.
You talked just in the first slide, like about the greedy algorithm, and you told us that
Yes.
basically your problem is too complex in order to have the variability of error estimator to do that.
Yes.
But I mean, is it a line of research in the sense, are there people that are trying somehow to find something, or like, in a simplified setting in order to then recover it for more different?
So actually, I'm not sure about the answer because I was not really interested in the greedy procedure. So I didn't really look into if there are recent results or papers talking about an a posteriori error estimator for FSI problems. And also, I mean, for the test cases that we considered, even in the parametric setting, like the geometrically parameterized test case, using an equispaced sampling, so that's like using a fake greedy algorithm, that was enough. Okay.
Okay, I see. Yeah, I mean, the problem is quite difficult, so I can understand completely the fact that it is not even a line of research, so it was like,
yeah,
no one is actually looking at that. Okay.
Yeah, but also because the POD performs quite well. So
well, okay, yes, of course. Then I don't know if Andrea wants to.
Yeah, I was unmuting myself for that reason. So can I ask a question, or is there anybody else?
Go on.
Okay.
Go on.
So first of all, thank you very much, Monica. The work is very broad. It's very interesting. The presentation was very good. In fact, I have a question. It's related to slide 18, where you basically explain how so what is your algorithm to
this one
exactly to obtain the conversion of your implicit step.
Yeah.
So if I take it correctly, and I might be wrong about this, you basically are trying to get a solution by fixed point iterations. Is it right? So you basically plug in the solution in point 1, and then the solution of point 1 goes to point 2.
Yes.
Okay. So how do you know it converges? Is it just because the time step is low enough and you know it does converge? Or
okay, so the reason for, so if you use this Robin transmission condition in the pressure Poisson formulation, then you are improving the stability of this sub-iteration. And there are a few papers that show you that. So this is the reason for using the Robin transmission condition. And then, of course, if you use a time step that's too big, then, I mean, that's not going to work. You will have stability issue and the two sub-problems are not going to converge. And also, let me tell you that in our test cases, so the two problems are like, they are linear, okay? So the two sub-problems are going to converge in very few, in quite a small number of sub-iteration. But I mean, if you consider, I don't know, nonlinear elasticity, so you change the kind of solid you are considering, then I expect the number of sub-iterations to be much higher. But so to answer to your question, using the Robin transmission condition improves the rate of convergence of the two sub-iterations. You can also use other like boundary conditions on the SSI interface here, like, I don't know, Dirichlet boundary conditions or Neumann boundary conditions, but you will have a little bit more of difficulties there. I don't remember in which paper they talk about this, but I know I read about it.
Mm-hmm. And so the ensuing question would be, and can you, or have you encountered somebody that does something different with respect to fixed point, and maybe they go with, I don't know, some Newton iteration in which they estimate the cross derivatives, the cross Jacobians, if you want, or something like that? Because that maybe can alleviate your problems with the time step. I don't know. I mean, I'm just, you know.
Yeah, that's
wondering.
true. No, I haven't thought about it, but that's true, because I mean, the problem with the time step, that's a big issue of the whole design, which anyway, apart from that, I mean, I really like it. It's still good, but yeah, the problem with the time step is quite important, I think.
Well, thank you. I was just wondering if, because like in some applications I have, which look a lot like FSI problems, fixed point, you know, in some corners I find a problem like this, and fixed point is not convergent. So first of all, I thought, well, that's a lucky, I mean, that's a positive situation. And so I had to go by, you know, through Newton iterations and things like that, and maybe so maybe the problem manifests itself through the time step rather than through not convergence. I don't know.
Yes.
But thank you.
You're welcome.
Thank you, Andrea, for the question. Are there other questions? Okay, so actually, I have another one, Monica, for you.
Yes.
Okay, and it is about this formulation, this Charinteman formulation.
Yes.
Okay, because actually it's something like, okay, I knew about it, but it's something that I do not use. And you list a lot of things, a lot of good things of this formulation, right? Like in the online phase, you have less space because you don't have to enrich your space and so on and so forth. But okay, but maybe actually, I don't know, maybe I'm a bit lost, but you clarified, I mean, these are a lot of pros, and I wanted like to clarify the cons, because it's not a thing that all the people that are dealing with Navier-Stokes equation use. Okay, so basically I wanted to understand why it's there, you can use it or not. Okay, or like why I am doing basis enrichment and you are not. Okay, this was my point. So I think that it's linked to the fact that you have to add these stability conditions and the delta T, right? Was this the point of
Yes. Yes. So are you asking me why I chose to use the Charinteman projection scheme?
Yes. And why am I not using it?
Okay. Okay. So, I mean, yes, for the reason for using this scheme for me was that I was interested in seeing the effect that it had in the online phase of the method. So as you mentioned, the fact that it has a lot of pros, which is again the fact that I do not need to use the supremiser enrichment, which is good, and also the fact that I can like solve a problem in the online phase, which is just related to the fluid pressure. So I have a problem just for the fluid pressure, which leads to a smaller system to be solved. But I mean, I mean, I don't know why you're not using. I don't have the answer to that. But also, there are a lot of things that are interesting about this method, even at the finite element level, and things that I still have some like question marks about it, because, for example, for my test case, you see, I was more interested in analyzing the behavior of the, let's say, of the structure with respect to the fluid. Okay, so for me, I was more interested in studying the bending of the leaflets. Okay, but if I'm interested in like focusing on the fluid problem, then for me it's still a question mark, like what happens to the end of step velocity. Like you have two velocities here, the intermediate velocity and the end of step velocity. But say you're interested just in a CFD problem, so just in a fluid problem. Okay, so the intermediate velocity is a solution to a viscous problem. Okay, but you know that that velocity will not satisfy a divergence-free condition, because you're not asking that. Okay, so I was like, yeah, when I'm looking at the results, is this a divergence-free velocity or not? Because the divergence-free condition just appears in the other sub-problem of the Charinteman projection scheme. And I don't know, I asked about that also in a CFD forum, but nobody replied. So it was either very stupid or very
or very complex. Okay. Yeah. Okay. Yeah. Now, very last questions. Very last question. It's actually about the last table of your last experiment. Let's see. Okay. Yes. Okay. The one with 800. Yes. Yes. Okay. This one, yes. But this capital NT is the snapshot, right?
Yeah, it's the number of snapshots for one parameter.
Okay, and it is equivalent to the number of time steps you took, or you basically sampled the snapshots?
Ah, no. Okay, sorry. No, so I use a training set for the geometrical parameters with 10 values for this range of the geometrical parameters. And then for each value of the parameter in the training set, I compute like 800 is the number of total time steps for one value of the parameter.
Okay, so my question now is why it is not 1000 and only 800, like the other test case?
No, that's just because it was a lot of
computational time.
Yeah,
okay, it is not a matter of the fact, I don't know, stability issues or
no.
Okay, only computational time. Okay.
Yes.
Okay, so thank you, Monica. It's
You're
enough
welcome.
for me. Thank you.
You're welcome.
Okay, so are there other questions for Monica? Okay, it seems not. So I thank again Monica, and I thank you for being with us, and we see We see each other next Friday. Thank you.